All right. All right, everyone. My name is Moiz Raja. I work for Cisco. I've been involved with the OpenDaylight project since Hydrogen, and I'm a committer on the controller project. And mostly I work on the clustering pieces, and that's what I'm going to talk about today. So before I start off, a word of acknowledgement to the people who have collaborated with me, especially to Tom Pantelis. A lot of work was done in this release, the Lithium release by Tom Pantelis, to stabilize the code basically and improve the performance of the clustering code. So I really like to acknowledge his work. But all the others, I mean, they've helped me a lot. My colleagues, Harman Singh, who's over here, and Kamal Rameshan, they've done a lot of work on the Raft and Datastore code. And a lot of good work done by Phil and Radhika and all in setting up the cluster, testing it, and stuff like that. So I acknowledge their work. I thank them for that. Here's the agenda for today. I'm going to start off with a few architecture slides, and mostly because everybody might not be familiar with the architecture of all our clustering, the clustering implementation that we have, the Akka-based implementation. And then I'll get into a little bit, somewhat of a dry topic, which is how the code is organized. Really, this session is about actually explaining how things work. And the goal is that at the end of this session, some of you might actually feel like contributing to the clustering code in ODL, or it might help you when you're building your application to debug issues and things like that. So that's why I'm actually going to go into some of the details. And if it gets too boring, just let me know so that I can skip a little faster. Some of it might be interesting. I mean, there's a lot of animations in the slides. Hopefully that'll keep you interested. But if it gets boring, let me know. I'll move a little faster. And I'll leave more time at the end for questions. So I'll start off with the architecture. So essentially, we have two subsystems implemented. If you remember the Yang, or if you've been to any Yang session, there are three components to the Yang. One is you have your data. So you have a schema where basically you specify what kind of data goes into your model. Then you have your RPCs, and you have your notifications. And we have implemented two things in the clustering implementation that we have. The first one is the Datastore. And the idea behind the Datastore implementation obviously is you allow for high availability, and you allow for scalability, where you have all these various members talking to each other, distributing the data, and somehow that works with the same kind of API that we have for, let's say, the in-memory implementation. And similarly, we have the RPCs. So if you have a routed RPC and you register it on any node, you want to invoke that RPC either from RESTconf or from any node in the cluster, regardless of where it's being invoked from. So these are the two subsystems that we do have implemented. The one which we don't have implemented is the notifications. I don't have a clear use case for that. So maybe I can talk with you guys and understand your use cases, and then we can see if we need to prioritize this for Beryllium. But right now I don't have a good use case for remote notifications. So these are the two subsystems that we do have implemented. And I'll go into a little bit of detail on this. Actually, how many of you already understand the architecture? Because I can go faster if you already understand. Because the interesting thing would be the flows, which will come on later. But I'll go into the architecture a little bit so that people are just familiar. All right, the next part is, what is this built on? So both the distributed data store and the RPC connector, they are built on, the foundation is essentially Akka. So everything is built based on Akka actors. And that is our way of actually ensuring that these components can reside on any node in the cluster. The actors can run anywhere. And you can invoke these actors or send messages to these actors from any node in the cluster without building in that intelligence of where exactly that actor resides. So that's what we use Akka for. And there is something common about these two modules. these are completely distinct modules. There's something common about it. There are things which are not common, and I'll go into the details of that. The distributed data store, one of the modules which it uses from Akka is the Akka persistence module. Now, sadly, when we started using this was an experimental module. So it's actually subject to change pretty quickly. And in fact, with the 2.4 version, there is an incompatibility which has been introduced, which we'll have to deal with in Beryllium. But right now, this is what we are using. And what Akka persistence gives us is the ability to store, the durability is given by Akka persistence. So you can store data, and then when you restart your node, you get back your data, and you reconstruct the state of your tree. And Akka persistence has two different things. One is it can deal with the journal, and the journal essentially is all the modifications that you ever made to your data tree is stored in your journal. The other thing is the snapshots, where the whole state of the tree is stored in persistence, basically on your file system. For the journal, we use LevelDB, which is a very fast implementation. We actually use LevelDB JNI. And because we use LevelDB JNI, on certain operating systems, it might not work out of the box. So there is talk of actually using LevelDB Java, but there is less performant. But I won't go into, I think I'm going too much into details. Anyway, so the idea is LevelDB is used for the journals, and the snapshots are stored on the file system directly. The next thing is Akka remoting, and as its name suggests, essentially it's a module where it lets one actor system on one node communicate with an actor system on another node. So that's basically the idea. And we also use Akka clustering, and that we use for discovery of the nodes. So for example, if you have two nodes, and you want to find out where the other node is, or what its IP address is, like where it's hosted or whatever, Akka clustering is what gives us that. And Akka clustering also gives us other things like, for example, is the member alive or dead, or is it reachable or not reachable, things like that. So these are the common, this is the common base that all these modules are built on. No. All right, so both are using actor systems. Now, one detail in there is both of these are using different actor systems. And why this is significant is because each actor system, the actor system is actually a pretty heavy thing. And what I mean by that is you have actor systems which host a actor hierarchy. So you have a hierarchy of actors where one actor could be like a supervisor for a bunch of actors, and those actors could be supervisors for other actors and things like that. So that you have a bunch of actors associated with it. There's some configuration associated with an actor system. So that tells you, for example, how your like which remoting port should be open for your actor system, things like that. And finally, you have the dispatches, and actually this is the heavy part. So this is your thread pool. Now, let's say I configure an actor system and I say, I want 16 threads to be used by this actor system. Now, if I have two actor systems, then I'll have 32 threads active at any given point of time. And that's what makes this heavy. And this might actually have been a mistake. We're trying to actually consolidate these actor systems. So right now we have two, but we'll probably have one in the future, so that both of these share the actor systems. The next thing which is common amongst these two implementations is data synchronization. The data store, it's kind of obvious. You have trees and you want the data tree to be synchronized. So essentially you have a big, like if you know about our Yang system and the way we actually store everything as a tree, we have a big tree of data, right? We have inventory, topology, maybe toaster or my app, or you name it, we've got that, right? Now we used to put that in one big tree, and we have to synchronize that tree, if for a high availability. And we have this data synchronization built into our data store, and we use an algorithm called Raft. I think you might have heard references to that before. we use that for consensus to make sure that all these trees look the same on each node. So that's basically the idea. But for RPC, it might be less intuitive as to what exactly are we synchronizing. So we synchronize the RPC registry. So on each node, you register. For example, if you have an OpenFlow switch, and it's exposing the AddFlow RPC on node 1, you want to know exactly how to invoke the AddFlow on that switch. And that information goes in the registry, and the registry is actually replicated too. But it's not replicated using Raft. We use a gossip-based implementation to distribute information about that registry across the cluster. The difference between these two is that Raft has a strong leader. So always the data distribution is always from the leader to the followers. That's basically how it works. Whereas with Gossip, each node talks to each other and then distributes the data. So Gossip actually works better when you have a very large cluster. Raft works well only with smaller clusters. So up to 20 clusters, 20 nodes in a cluster is okay with Raft, whereas with Gossip you can go up to 400 nodes. A little bit more detail about distributed data store. So what's the main idea behind distributing data? If you have two members and you have a client on one node and you have the data on another node, like you have member 1 and member 2, client is on member 1 and the data is on member 2, and you want to just access that data. And how do you make that possible is basically what this implementation is all about. So what we do is we actually put in a proxy object where the client is accessing the data. So that's what we call distributed data store. So that if you go and look at the implementation, you will find a class called distributed data store, in fact. And if you look at the implementation, that's what guides you as to what is the next step, what will happen when you invoke, for example, if you try to create a transaction on distributed data store. So now this distributed data store has to talk to the data tree which is on member 2. And how you make it happen is, well, come one slide later, but essentially distributed data store, I mean this is like a filler slide, but distributed data store is an implementation of DOM store. It's an SPI. I think some people are familiar with that because they're trying to build their own data stores. If you want to build your own data store, you have to implement this SPI interface. And distributed data store is one of those implementers. In-memory data store is another implementer. The data tree is a consistent data tree. So what that means is once you write the data in and you do a subsequent read, it should be there. Whereas with Gossip, it's an eventually consistent mechanism. So it may or may not be there, but sometimes you don't care. Like for RPCs, maybe you're willing to tolerate that. For data, we can't. Right. So going back to this, how the distributed data store communicates with the data tree. Well, actually, I've got this it's showing up pretty light, but there's a box around this, the data base or that symbol. So we put an actor around that data tree, essentially encapsulate the data tree within an actor, so that when you want to communicate it with that data tree, you just send messages to the actor, and that message is processed by the actor, and that modifies the data tree. So that's essentially how this works. So the communication, we use ACA for communication, essentially. The next thing is the data distribution. So once you are able to access data remotely, the next thing you want to do is you don't want to have all your data in one place, right? So you have this big data tree, inventory, topology, toaster, foobar, whatever, you put everything into the data tree, and now it's become a big data tree. It's become so big that it doesn't even fit into one node because there's not enough memory on that node. So what you really want to do is break it up into smaller trees, onto subtrees, and you want to distribute it across the cluster. So this is this also works with this implementation, where you can have inventory on member 2, you can have topology on member 3, and if you actually have a larger cluster, maybe inventory is on a subset of that cluster, topology is on a subset of that cluster, and things like that. So this is again about the same thing. If you have the big tree, you need to break it up, right? So essentially what we do is, at the module level, we break it up. So you had the root level, and you had inventory, topology, and toaster under that. Now what we did is we just took inventory, topology, and toaster and put it into its own shard. Now we can do that, so we can have module level stuff, but what happens to the rest of the data? What happens to foobar? What happens to my apps data? That has to go somewhere. So for that, we have this default container. And if you go and look at, if you just run the controller and you go and go into JConsole and you look at, I'll show you what to look at. But you'll see there'll be one shard in there, and its name will be either default config or default operational. And that shard actually contains the rest of the data, so everything else. Today, there is no way to actually say that store inventory and topology data in one shard, which might be a feature which we might need in the future. But this is what we have for now. All right. So the next thing is high availability. So I'm able to distribute my data. I can have inventory on one node, topology on another node. But what if I had inventory on one node and that node failed? Then would I lose my access to my inventory data? I don't want to lose access to my inventory data. So essentially what I do is I distribute that also across the cluster. I replicate it, essentially. And on member 1, I have the leader of inventory. And member 2 and member 3 are 2 other followers which have the exact same data, so that if member 1 was to go down, then one of the other 2 nodes would take over as leader. And you'd have high availability that way. And how exactly that works is governed by the Raft algorithm again. And this is essentially what, these are the 2 basic things in Raft. One is you have the election. So when you start up, when a shard starts up, it's the follower. It starts up as a follower. So it does, because it doesn't know about anything else in the system, so it just starts up as a follower, and then it waits for some time. It waits for about 10 heartbeats, let's say. And if it does not receive any heartbeat from the leader in that time period, then it becomes a candidate. And again, it waits. Well, actually, it waits, but it waits after sending a request for a vote. So it says, well, I am on term 5. I want a vote from the other people or other replicas. And of course, it votes for itself. So once it gets, if it gets a vote from, let's say you have a 3-node cluster and you get a vote from one other node, then you become the leader. Otherwise, you stay candidate, and maybe you start up another term. If you get a request from the leader, then, well, then you give it the vote and you remain a follower, something like that. Once you become a leader, then you have the authority to replicate data to the other nodes. So you start replicating. So over here, the leader replicates sends these append entries messages. And append entries serves both as a heartbeat as well as a way to replicate data. So it's like a 2-in-1 thing. And that's how the replication works. The consensus, how it works is, so if you have a leader and you have 2 followers, you need to be able to replicate to at least one follower and receive confirmation from that follower before you say, well, this is okay data. And then you can commit it, then you can put it into the tree. If you don't get that response, then you cannot actually put it into the tree. So it just stays in your journal. Am I making sense?
Question about transitioning from when you lose your leader. Is there a quicker way to force leadership to a different node? Do you have to
No, you just have to kill that node.
kill it and then wait?
Yes. That is the only way right now. There are other ways which we are exploring. So there might be a it's coming under the guise of 2-node cluster or something, where what we will do is we will say, okay, disable all elections, all the Raft elections, so that I can choose the leader externally. But once you take away that from the Raft, the Raft implementation of elections, then you have to be sure about who you're setting as the leader. But that's a topic for discussion, I think on Thursday or Friday, under the two-node cluster or multi-data store clustering implementation.
The use case, you need to bring somebody down for maintenance.
Mm-hmm.
You don't want two candidates or two followers, for however long it takes. You want it immediately to fail over.
Yeah, so it will fail over, obviously, but it'll take 10 seconds for it to fail over. Now, that is a configurable thing. By default, it'll take 10 seconds. You can make it, re-elect a leader faster, but by default, it's 10 seconds.
So applications need to be aware that it could take 10 seconds.
Application need to be aware. Actually, we do have an exception which gets thrown at the point where, like in that 10-second time period, if you do try to do something, an exception will be thrown, Datastore unavailable, and then you can handle that. All right, this is going to be an animation which will move pretty quickly, so please watch. So this is just demonstrating that when you have a transaction and it gets replicated, you just need to have one other node get that transaction before you can confirm that, okay, turn green, put this into the data tree. You don't need to have them replicate to both the nodes. In fact, I could say you can take away follower 2 completely and you still would have the transaction committed. However, you will not be able to tolerate follower 1, for example, like after follower 2 is down, if follower 1 also went down, then you will have no other commits happening. You can have transaction 5, transaction 6, all those transactions can keep coming in and they'll be put into the journal, but they will never be applied to the tree. That is if leader remains. Of course, if it was follower, the transactions itself will get rejected.
So if the leader dies and only follower 2 has the transaction, what happens then?
If the leader lies and only follower 2 has the transaction, then follower 2 will actually become the leader.
What if it doesn't become a leader?
It will become the leader because what happens is with Raft, there is this election property where let's say even if follower 1 became a candidate before follower 2, and it will request a vote from follower 2, and it will say, okay, I have 3 transactions, and so my commit index is 3, and my term is let's say 4. It sends that. This guy checks, okay, you have a higher term, so you can become a leader, but your index, the number of entries that you have in your journal are less than what I have. So you cannot become the leader. So it will reject the vote. And then it will become a candidate itself. And it will request a vote. So when follower 2 requests a vote, it will get the vote because it has a longer log. And these are all properties of Raft, essentially. All right, so the other thing is, now we have these append entries happening and the journal is being replicated one entry at a time. But typically when you bring up a node, you don't want one by one the entries getting replicated and getting into the log because it takes too much time. So essentially what we have, and this is not, this is a general solution, but I'm explaining it in terms of restarts. So when you restart the node, when follower 2 comes up, instead of sending it append entries, we just send it the snapshot. So the whole data tree is sent as a snapshot. And what we do in addition is we actually break up, because this data tree can be arbitrarily large, so we break it up into smaller chunks and we replicate it. So we break it up in 2 megabyte chunks, which is configurable, but essentially that's what we do. And the main reason for doing that is because Akka has some limitation in terms of how large the message can be. Finally, we have durability. I explained this earlier that the data tree, there is the data tree which is in memory, but there's also the journal which is persisted. And the reason for this is when you restart, you have to recover from persistence. Like for example, if you have configuration data, you've added a bunch of flows into your configuration. When you restart your controller, you want to see all those flows in there, because otherwise you won't be able to reconfigure your switches the same way. So the level DB journal is essentially all the modifications that were ever made are stored in the journal one by one. And the snapshots you have because, again, you want to recover faster. Let's say you have 1 million flows in your journal. You don't want to wait like a long time for each like each flow to be read from disk and then be put into your data tree in memory. You just want to put the whole data tree into a snapshot, which is a disk file, which will be read all at once, and the tree will be constructed from it. So that's what this durability part is for. It's to help with recovery. So, any questions on the architecture on distributed data store?
Probably going to go nowhere, but if someone was looking at a large enterprise where, for instance, they had OpenStack, or maybe they even had Cassandra as an enterprise distributed data store, what would you tell them? I have to add a third distributed data store. So what value does akka provide over perhaps Swift from OpenStack or Cassandra?
See, first of all, there is no additional data store that you have. This is like this data store is core, like it's runs in the same VM as your controller.
Okay.
So you don't have to install an additional component. Actually, in fact, that is one of the the pros of this whole thing. That you don't have to install anything else. You just have to, all you need to do is run your controller, and you can have a distributed data store package along with it. But if you do have Cassandra, and I'm sure people will, what would be the disadvantage of using Cassandra is, every time you make a modification to your tree using the MD SAL API, you would have to send that data over to Cassandra. So essentially, your transaction would have to be committed onto Cassandra. So you'd have to serialize your data. And since we have this whole thing under control, we actually do something which makes modifications, like local modifications, much faster. So we avoid that whole serialization for local transactions, and I'll come to that. So there's a flow in which I'll talk about it. Anything else? I have 23 minutes, I need to rush. All right, so invoking RPC is about the same thing. Earlier we had member 1, member 2, we were trying to access data. Here we have member 1 and member 2, where consumer is on member 1 and the provider is on member 2, and this somehow has to work. So again, how this works is, we have a proxy on the consumer end, which understands how to route to a remote broker, which is on the other end. And that is done by actually I'm skipping something. Remote RPC broker here is actually an actor. Okay, so the RPC provider can actually send it messages. So whenever it wants to invoke it, it just sends it a message, and then the remote RPC broker gets that message, it interprets that, and it calls the appropriate method on the provider. The RPC registry is populated this way, that if you have a provider and you register your routed RPC, when you register the routed RPC, we have an RPC listener in the remote RPC broker which actually gets invoked. So it gets called. That way we know that somebody has actually registered an RPC. So it's an internal mechanism. Actually, other people can use it too. But anytime somebody registers an RPC, we get notified. And when we get notified, we add that information to this RPC registry. So this bucket, essentially. And this bucket is what gets replicated. Now the RPC replication uses this gossip mechanism where anytime something changes in this bucket, we actually change the version of that bucket. So for example, let's say as a switch is connected to one node in the cluster, like OpenFlow 1, let's call it OpenFlow 1. That registers, and because it registers, you have to register an RPC for it. Let's say an add flow RPC has to be registered. When you do that, you register the RPC, we get invoked, RPC listener gets called. That in turn modifies the bucket for that particular node. And once it's modified, we change the version. And once the version is changed, then that is eligible for replication. Because the other nodes would not have a bucket, essentially all the information from that particular node will not have, it will not have that particular information because it has like an older version of the data. And kind of works like this. each node has the bucket information for all the other nodes. So member 1 will know, for example, that on member 1, I have version 1 of the bucket, member 2 I have version 5, member 3 I have version 7, and so forth. And this information is replicated to all. This way, when I send the bucket over, or basically I do a gossip with the other nodes, then I can tell, okay, I have an older version, so I need to request a newer version from the other node, something like that. So the gossip mechanism works like this. Every second, all the members send status messages to each other, and essentially that is telling, okay, I know of these versions of the buckets. And then based on that information, the nodes can actually say, well, send back a status. If they have, like, if the version is lower, then it sends a status. Otherwise, it sends an update. Well, I think this is actually too deep. I'll have to go. I have to talk much more about this if I have to explain this thing. But I'll skip this. What do you say? So the idea is this. I mean, if the bucket information, like this is like just every object is versioned, and if you have a newer version of an object, you basically send it over to the other node. If you have an older version, you request it from the other node. It's as simple as that. Okay?
So you said that all nodes know what the version is in all the nodes.
Yeah. So that's because they keep exchanging the status message every 1 second. Every second they say, okay, I think these are the version. This is the version information that I have.
For all the nodes.
Yeah, they keep sending to one arbitrary node. They don't send it to every node. So member 1, for example, right? Member 1 sends its status message only to member 2, and member 2 sends it to member 3. See, it's not like member 1 is sending to both to member 2 and member 3. So any one node. And when they send that message, the other node can say, well, my version is higher, so here's a new version. If it says, well, if it gets a version which is lower, then it says, okay, send me another, it sends a status again. When it sends a status and the other guy gets a higher version, then, well, it updates it. So that way you keep exchanging.
When they're communicating between themselves, they inform of all the versions they know about, not just their own version.
Exactly. Yeah, actually this kind of poses one challenge which we will tackle later, that right now the version is on each bucket. So the whole registry, the registry can actually be pretty large, depending on how many RPCs you're registering. So we will try to fix this in a later release. I'm going to talk about modules. Yeah. Sure.
On the previous slide about providers and clients, can there be multiple instances of the provider? And in that case, how would we know the RPC?
Well, you actually, when you register an RPC, you have to give a specific identifier for your RPC. For example, let's say you have multiple switches, right? And all the switches have an add flow that you can invoke, but you need to distinguish them somehow, right?
If they are equivalent, just for redundancy, I have replicated my provider on 3 nodes.
Mm-hmm.
So in case one node fails, another instance of that provider can act on the request.
Mm-hmm.
How would I use RPC?
Both of them would not work. The last one will win. The last update will essentially win. So you cannot have, when you call add flow on the same switch, like OpenFlow 1 switch, let's say, it's not going to call RPCs on 2 different providers. It's going to call only on one provider, which is the latest that was registered.
So I cannot have like a replicated provider for multiple nodes.
You can, but it wouldn't do you any good. Both of them registering for the same switch is not going to do you any good, for example.
Yeah, switch is a bad example.
Some other thing. I think what you're talking about would be more useful for a publish subscribe kind of mechanism, which is the Yang notification mechanism, and we do not support remote Yang notifications today. We can talk about the use cases where that would be helpful, but we haven't discovered them yet.
Question?
Yeah.
So, do you provide any kind of API if we want to dump the current state of the registry and also
Yes. Yes, there is an API. I'm going to talk about that shortly. Actually, I'd like to rush through these modules thing because I really have less time. But this is essentially talking about how the code is laid out. If you're really, I mean, you can look at the slides and you can determine what they do. So the main thing, the main components are SAL Clustering Common, SAL Raft, SAL Distributed Data Store, and Remote RPC Connector. The others are like peripheral to it. Look at that code, look at these slides, and you'll see what exactly is in there. That way I can go on to the flows. Is that all right? Okay, so for data store, I'm just going to talk about what actually happens, like some simple flows like startup, shutdown, or transactions, what happens, so that you can actually follow the code. And the class names which I mentioned, these are real class names. You can go ahead and look up on your IDE, and you can know that that is your starting point. So for example, like with the data store, right, there are two modules, in fact. There are two data stores. There's a config data store and there's an operational data store. So you will see two modules in there. One will be called distributed config data store provider module, and one will be called distributed operational data store provider module. So those are your starting points. And when it starts up, there's a create instance method in each module which gets called. Now, when you call create instance, it creates an instance of the distributed data store. This is where it starts off. So we call create this instance, and then we wait till it is ready. So if you're familiar with the config subsystem, when you have a module and a create instance is called on that, you're supposed to return an auto closable, and then the config subsystem moves on, it creates other modules, and then it wires it in with other modules, and so on and so forth. But when you have a distributed data store, how do you know that it's ready for use? I think that's a problem to solve. Because with in-memory data store, it's quite clear. You create the in-memory data store, it's immediately available for use, you can start creating transactions and so on. But with distributed data store, you cannot tell, because if I just start off one instance of the controller and the other instances are not started, then consensus will not be there as to who is the leader. So it will start off, it will be a follower or a candidate, and so, well, there's no leader found. So if no leader is found, I cannot create a transaction, right? So this is an attempt where what we do is we go ahead and create the distributed data store, and we have this wait till ready latch, which we have. And over there, we wait for 90 seconds to find a leader. And essentially, that's like you start off another node, and that node starts off, the shards are created, the shards go ahead and elect a leader. And if that happens within 90 seconds, then we move forward. The countdown will be done on the latch, it will be cleared, it will move forward. Otherwise, it will block for 90 seconds. And well, it won't wait forever, it will be only for 90 seconds. So once we do that, once you create the distributed data store, the distributed data store creates these two classes. One is the actor context, which allows you to actually communicate with the actors, because distributed data store is not an actor, whereas actor context is. And it also creates another actor called shard manager. This is the parent of all the shards. The shard manager is what creates all the shards. So what shards it creates is based on a configuration file called moduleshards.conf. And this information is there in the wiki. So in this case, it would be like shard 1, shard 3, shard 4. These are the 4 shards that gets created. Now, for all these shards, we need to find a leader. And if we don't find the leader in a timely manner in 90 seconds, then we will move forward anyways. But the result is that if transactions were to be created without the leader being found, all those transactions will fail. There is a retry mechanism, but they will fail. They might fail. Now, when the shards are created, the first thing they do is they have to recover from disk. And this is only if they are persistent shards. So the config data store, this is going to happen. First, it will read its state from the disk. It will go ahead and construct the tree, and once it's constructed the tree, then it'll basically go ahead and set its behavior. It'll say I'm a follower now, and I'm ready for communication. So then the process of election and all that happens, and then the leader is chosen. But the first thing that needs to happen is recovery from disk, and which happens either from the snapshot or snapshot plus journal. Now once the leader is found, the countdown on the wait till ready latch happens, and we move forward. Now for both config and operational data store, this needs to happen. This I won't go through because it's just restating this, whatever I just said. Now the next flow I want to go through is the creating of a transaction. So once you have everything ready, you have a distributed data store. In fact, even if it's not ready, you have a distributed data store. You can go ahead and create this new transaction on it. Now if you look at these methods, this new read-write transaction, all these methods, some of these methods might not be familiar to you because you might be using it from the binding aware broker perspective, and some method names are different for the SPI. But if you create a new transaction, what we do is we create an object, an instance of transaction proxy. Now transaction proxy, we create a transaction proxy because when you create a new transaction, there is no way for me to tell exactly which data tree you want to affect, right? You just create a new transaction. You never told me I want to do a transaction on inventory or topology or whatever. You just create a transaction proxy. And it doesn't actually talk to any shards. But later on a transaction proxy, you might do an operation. For example, you say, I want to write inventory node. Now this is when we actually figure out, okay, you want to do a transaction on inventory because you tried to write to inventory node. And that's when we actually go ahead and seek, we try to find the primary replica of the inventory shard. So once we find that primary, either by looking up in the cache or actually doing a shard manager find primary. I mean, these are two cases which maybe I shouldn't get into. But if it is found, then we create, if it is not found, we create a no-op transaction context. And this is just a dummy transaction context which will fail on commit. If it is found, then we check whether it's a local transaction or it's a remote transaction. Now I'll show you what it implies, what remote transaction implies, what local transaction implies. But if it's local, then if it's not local, then we create a remote transaction context. Otherwise, we create a local transaction context. And these are names of classes that you can look up to. So what is a local transaction? If you have a client which is located on the same node as the inventory leader, then you have a local transaction. If you have a client which is remote to your inventory leader, you have a remote transaction. So that's basically the distinction between the two. And this actually has repercussion on performance because of the way we actually deal with remote and local transactions. So we actually optimize for local transaction, and this is kind of how it works. So let's say you determine that your shard leader is local. So you've created a local transaction context, right? Now you're going to do some operations on it. So before you do any operations, the local transaction context steals a reference from the shard of the data tree. Basically the data tree is available on the local transaction context as just an object which can be interacted with. So now I don't actually have to send a message over to the shard leader. I have a reference to the data tree, so I can actually modify the data tree locally. And once you do that, then any operation that you do on the transaction context is directly done on the data tree right there. So write, merge, delete, ready, and it's disappearing, but essentially what happens is when you commit it, then the commit is sent over as a message to the remote shard. But since both of them hold the reference to the same object, they can work with it. So that's basically how local transactions work. For remote transactions, obviously we cannot steal a reference because this, like you have member 1 and member 2, the remote transaction context is on the client, and that's remote. So you don't have a reference to the tree. So the only optimization that we can do over here is when you make modifications, we collect the modifications locally into a list. So here we did a write, we said, okay, put that into the list, merge, put that into the list, so on and so forth. And you just collect a list of all the modifications that you want to make. You're not sending it over immediately, you're just batching them. And once you go ahead and do a ready, that's when you send all the whole batch over to the other side, and you go ahead and update try to update the tree, but something like that. That makes sense? It's batching, using batching as an optimization. Now, what this tells us is, if you have a local, if you can somehow do a local transaction, it's going to be better for you, because you're doing an operation, all the operations are being done on the data tree. So that's going to be the fastest way to actually update your data to a transaction. But if you cannot do that, if you do have to have your data tree remote, then you should try to avoid doing any reads on that data tree. Because I'm showing ready over there. The ready and read is the same thing. Actually, there's a separate method called ready. What it does is it prepares the transaction for committing. So that's what ready does. But read actually goes and reads from the data tree. Now, if you call read, then it'll actually, a message will have to be sent to the remote node. Everything that was done before that has to be sent to the remote node. It has to change a snapshot, and then only then can the read be satisfied. So reads are going to be really slow if they are remote.
So how is consistency maintained if there are two different nodes modifying the same object and then they read locally?
They're not modifying the same object. In fact, well, this actually goes into how exactly our data tree works. So when you create a transaction on a data tree, it doesn't modify the data tree at all. So you essentially get back a snapshot of that data tree, and you can do any modification you want to that snapshot. And only when you are satisfied with all your modifications, you can go ahead and commit it, which then updates the final tree. Or you can just throw it away and nothing changes. So when I say when you do a ready and everything goes over to the other end, what we are really doing is we send this message, the batch, to the other end, we create a snapshot, and we make the modifications on that and prepare it for commit. 2 minutes. All right. I have just 2 minutes left. So I'm actually going to skip over to all this stuff and talk about diagnostics. I think I probably need a much larger session for this, or a longer session. Because you'll need to diagnose the issues, right? So I think I'll need to start with that. So when you do transactions, I'm skipping all this stuff, but if you have questions later on, we can talk about this after the session. I think I prepared too many slides. So this is about tracing a transaction. If you have a transaction and you want to figure out what's actually happening with the transaction, monitor the log messages. Because we actually put in some information in each log message which tells you what exactly is happening with your transaction. For example, on the client side, when you create a transaction, you'll see a log message on the client log. So on, let's say, member 1 was the client, you'll see a message which says, created transaction member 2, transaction some number of type, whatever is the type of the transaction. And this is what it actually means, that this transaction was created on member 2, that is the initiator of the transaction. The counter of the transaction, this is the 9400 transaction that was created, and it's a read-write transaction. So that's what it means. Then once you try to do an operation, again, the same thing is printed now. We also print exactly which type of data that you're actually trying to read, for example, in this case. Then on the server side, you'll see something like this. Member 3 shard inventory operational creating transaction shard member 2. So here what we are saying is the leader, this inventory is the module, inventory operational, and member 3 is where the leader is. because otherwise this transaction creation request wouldn't have ended up over here. Like create transaction always goes to the leader. That's why it's ended up over here. Then you have the data store type. Well, sorry, the arrow is pointing to the wrong location. It's operational really. So once this is done, on the other side, when you try to commit the transaction, you'll see something like that. Transaction member 2 readying one transaction for commit. On the server side, you'll see readying transaction member 2 transaction 900, and transaction member 2 commit on the client side, committing transaction on the server side, commit succeeded, and that would be the end of the transaction. Similarly, you can trace replication. So this is when append entries are happening. So from the leader, you'll see something like this, sending append entries to follower. On the follower, you'll see something like this, like the append entry arrived, and it's been handled, and the leader got back the append entry. So you can trace any replication issue, you can go ahead and trace this way. Now the other diagnostic capabilities we have is the beans that we have. So this you can monitor using JConsole if you want to, but I put down the name over there in the same convention that you would use for example, if you're constructing a Jolokia URL. So essentially this is for the distributed operational data store bean, where what you're actually monitoring is the inventory operational shard here, the member 1 inventory operational shard. And this is what you will see on member 1. On member 2, it will be member 2 inventory operational shard, and so on and so forth. And there's a ton of information that you can get from here, including things like, what is the current commit index, which was the last index which was applied to the log, who is the leader, what is the RAF state of that particular replica, and so on and so forth. You should try launching one instance of the controller and going to JConsole and checking it out. There's a lot of information there. Similarly, for shard manager, you can tell what are the local shards, whether the current data store is in sync with the other data, like the replicas, and so on and so forth. Then there is some runtime information which tells you what is the current transaction creation rate limit. Unfortunately, I didn't have time to go through the rate limiting behavior, but we actually limit the number of transactions that you can create. It's just a back pressure mechanism so that like any client, no client can overwhelm the data store. We also have operation limiting. That means you cannot do more operations than what the data store can handle before applying it to the state. But that is not, there's no way to monitor that. And then we have a bean which actually tells you the details of the commit rate. So how quickly are transactions being committed? What is the 50th, how many have been committed? What is the 50th percentile, 75th percentile, so on and so forth. Did I repeat something? And then we have a bunch of beans which give statistics about each and every message, each and every ACA message that actually occurs in the data store. And this is something which is common with the RPC as well. So I think somebody had a question about can we access, what kind of information can I query about remote RPCs, about the RPC registry? So if you go to the remote RPC broker, it has a couple of operations like this find RPC by name or RPC by route. So you can go ahead and query as to whether that particular RPC has been registered or not, as it's there in the registry or not. And finally, the same message statistics are also there. There are beans for each and every message statistic. Now, any questions? Dynamically adding and removing nodes is not there. So we haven't implemented certain portions of Raft which allow you to add and remove, like basically join and leave, right? We haven't implemented that. Something that we're targeting for Beryllium. Other questions?
Do you have REST configurations to configure
REST configuration for configuring what?
members?
No, right now the only way to configure it is using a configuration file. There's a module shards conf. That's how you specify, for example, which shards you have. RPC does not require any additional configuration. But the rest of the stuff, well, actually, the data store configuration itself, we do have like a CFG file which contains all the configuration that you could possibly do. We don't allow you to change it using REST or anything, but you can actually view it using JConsole. That's basically what one of the beans actually does. It shows you the configuration. There's another question? Yeah.
I guess my original question you kind of answered. I was wondering whether your clustering is only static configuration only. I guess you just answered it. It's just static configuration for now.
For now, it's static configuration, yes.
Yeah. So what happens to the device side if it is an OpenFlow-based device or NetConf-based device? How do you do like clustering to avoid one connection to one node gets failure, and how do you protection that connection to a separate?
Right now, we actually don't have OpenFlow clustering. We don't support something like that. For that, we would have to have some API which could actually give us the leader for a given switch so that you can gain mastership, because that's how OpenFlow 1.3 works, right? If you have the same switch connected to multiple instances of the controller, one of the instances has to take over as master. And that can only happen if there was some election mechanism amongst the various instances, which we don't have today. I mean, the data store has it, but it's not exposed as a service. Yeah.
Have you measured transaction rates?
Yes.
Are you happy with them? Improvements?
So we've been running DS benchmark against 3-node clusters. I have various numbers. So we're doing about 30,000 to 100,000 transactions per second based on the DS benchmark numbers in a 3-node cluster with replication.
Unrelated question, in the batching, since you do a local copy, you fail the entire batch if there's any kind of a conflict. So
If there's a conflict, yeah, you would.
you don't have to state recover from.
No. Well, what would you do if you had a larger cluster? That's a question. In what use case do you have today? I mean, you want to support a lot of devices, like IoT kind of thing. So you want to support large scale. Well, we need to build in more primitives before you can even make that happen. Because even if you had all those devices connected, where would you put the data? Is that going to go into like one big module? All the data goes into one module? Because updating that one module obviously will have limitation. You have one actor which essentially gets all the updates for that, so it's all queued up, because that's how the actors work. For each actor there's a queue, and every update will get processed in sequence, one by one. So that is not going to scale. We'll have to come up with some way to micro shard it, like break up that shard into smaller shards so that you can update the data. But once you have micro shards, then you have, like you have to be able to aggregate the data in case somebody does a query. So all those other problems have to be solved before we can even reach there. So for beryllium, and actually maybe even for lithium SR, one of the SRs, we first want to solve solvable problems like OpenFlow clustering, NETCONF clustering, things like that. So specific applications. And then maybe open it up to like general solutions, like IoT kind of things. I think you should experiment with IoT with single node for now, for best performance. More questions? Pardon? Yeah, They'll be available. I mean, I'd be happy to go through them with you. I think I underestimated the amount of time. Anyway, I'll of course upload them to the OpenDaylight wiki. More?
Yeah, when you mentioned write, merge, delete, followed by a ready, is that what you mean by transaction chaining? Or is that something else?
No, I actually haven't even started with transaction chaining.
Oh, okay.
That would be a whole different. I think I'll need a whole session for that. But when I say ready, see, that's what ready is an internal. It's an SPI method. When you're building an application with a binding aware broker, you actually you never know about ready, because what you're essentially doing is you're creating a transaction, and then you're doing a put or a merge on it, and then you're submitting the transaction. So those are the methods, right? What this,
Submit equals ready. Ready
yeah,
comes with done.
yeah.
Dividing cycle is called submit. So submit is ready.
Submit, yeah. As soon as you do submit, we do a ready, but then it goes to like pre-commit, commit. That's something which happens on the back end. Some things which we need to actually streamline more, but.
Do you provide any hooks for persisting the data outside of, like if you want to use our own database?
Yeah, you can do it actually. So ACA persistence itself is pluggable. So by default, we are using level DB, and the file system is where we store the snapshots, but you could actually store it somewhere else. However, remember that we still would use Raft for replication.
Why didn't we replace that? I want to make a copy of the persistent.
Is the next session about to start or something? Okay. All right, I'll have to take it offline. Sorry. Thank you. Okay. One is you have your data. So you have a schema where basically you specify what kind of data goes into your model. Then you have your RPCs, and you have your notifications. And we have implemented two things in the clustering implementation that we have. The first one is the Datastore. And the idea behind the Datastore implementation obviously is you allow for high availability, and you allow for scalability, where you have all these various members talking to each other, distributing the data, and somehow that works with the same kind of API that we have for, let's say, the in-memory implementation. And similarly, we have the RPCs. So if you have a routed RPC and you register it on any node, you want to invoke that RPC either from RESTconf or from any node in the cluster, regardless of where it's being invoked from. So these are the two subsystems that we do have implemented. The one which we don't have implemented is the notifications. I don't have a clear use case for that, so maybe I can talk with you guys and understand. All right, everyone. My name is Moiz Raja. I work for Cisco. I've been involved with the OpenDaylight project since Hydrogen, and I'm a committer on the controller project. And mostly I work on the clustering pieces, and that's what I'm going to talk about today. So before I start off, a word of acknowledgement to the people who have collaborated with me, especially to Tom Pantelis. A lot of work was done in this release, the Lithium release by Tom Pantelis, to stabilize the code basically and improve the performance of the clustering code. So I'd really like to acknowledge his work. But all the others, I mean, they've helped me a lot. My colleagues, Harman Singh, who's over here, and Kamal Rameshan, they've done a lot of work on the Raft and Datastore code. And a lot of good work done by Phil and Radhika and all in setting up the cluster, testing it, and stuff like that. So I acknowledge their work, thank them for that. Here's the agenda for today. I'm going to start off with a few architecture slides, and mostly because everybody might not be familiar with the architecture of understand your use cases, and then we can see if we need to prioritize this for Beryllium. But right now, I don't have a good use case for remote notifications. So these are the two subsystems that we do have implemented, and I'll go into a little bit of detail on this. Actually, how many of you already understand the architecture? Because I can go faster if you already understand. Because the interesting thing would be the flows, which will come on later. But I'll go into the architecture a little bit so that people are just familiar. All right, the next part is, what is this built on? So both the distributed data store and the RPC connector, they are built on, the foundation is essentially akka. So everything is built based on akka actors. And that is our way of actually ensuring that these components can reside on any node in the cluster. The actors can run anywhere. And you can invoke these actors or send messages to these actors from any node in the cluster without building in that intelligence of where exactly that actor resides. So that's what we use akka for. And there is something common about these two modules. These are completely distinct modules. All our clustering, the clustering implementation that we have, the akka-based implementation. And then I'll get into a little bit, somewhat of a dry topic, which is how the code is organized. Really, this session is about actually explaining how things work. And the goal is that at the end of this session, some of you might actually feel like contributing to the clustering code in ODL, or it might help you when you're building your application to debug issues and things like that. So that's why I'm actually going to go into some of the details. And if it gets too boring, just let me know so that I can skip a little faster. Some of it might be interesting. I mean, there's a lot of animations in the slides. Hopefully that'll keep you interested. But if it gets boring, let me know. I'll move a little faster. And I'll leave more time at the end for questions. So I'll start off with the architecture. So essentially, we have two subsystems implemented. If you remember the Yang, or if you've been to any Yang session, there are three components to the Yang. There's something common about it. There are things which are not common, and I'll go into the details of that. The distributed data store, one of the modules which it uses from akka is the akka persistence module. Now, sadly, when we started using this was an experimental module. So it's actually subject to change pretty quickly. And in fact, with the 2.4 version, there is an incompatibility which has been introduced, which we'll have to deal with in Beryllium. But right now, this is what we are using. And what akka persistence gives us is the ability to store, the durability is given by akka persistence. So you can store data, and then when you restart your node, you get back your data, and you reconstruct the state of your tree. And akka persistence has two different things. One is it can deal with the journal, and the journal essentially is all the modifications that you ever made to your data tree is stored in your journal. The other thing is the snapshots, where the whole state of the tree is stored in persistence, basically on your file system. For the journal, we use LevelDB, which is a very fast implementation. We actually use LevelDB